We've made it to the last topic in our chapter, and I want to just again give you a big picture where we at here. So we talked about bonding, we talked about Lewis structures, we talked about having the correct shape for a water molecule, and now we're going to add these arrows on here to talk about polarity, okay? And that polarity then will inform what we do in the next chapter and future chapters where we talk about the function and the properties of all kinds of things, carbs, proteins, viruses. There's elements of polarity that play into the behavior of all of them. And just one more big picture thing, all the way back to our very first slide in this chapter. This was sorting through the terms. So remember, we've been talking about matter, pure substances, and compounds, where we have two different elements. And what we've been focusing on with all these Lewis structures and shapes are the molecular compounds. We also had talked about ionic compounds, where we just have charges. Here we've been sharing electrons, and we have worked our way through Lewis structures, shape, and now we are at polarity. So we've accomplished a ton in this chapter. If you're feeling like it's been a ton, it has been, all right? So hang in there and let's learn about this polarity piece so we can start to do some cool things in future chapters like function and properties. So when we talk about bonds, a few things I want to have you keep thinking about. We're going to be talking about electron pairs and electrons. We will be talking about electronegativity again, which we saw back on slide 4, I believe. And we'll be talking again about those ionic and covalent bonds. Also, you'll see me using some colors here. When we talk about if a molecule is polar on the next couple slides, we'll see pink. And then bond dipoles, we will be using this little blue arrow, which we'll talk more about in a moment. So if we take a molecule like water, okay, so far we've been assuming, and assuming is okay until data proves you otherwise, but assuming that when the atoms in a molecule are covalently bonded, right, they're sharing electrons here, we're assuming that this is an even share. I get them, you get them, it's a 50-50 kind of even sharing, and that there's no charges here. And then in contrast, at the beginning of the chapter, we had talked about an ionic compound where electrons are not shared at all. So let me just pretend that this is an ionic compound. The chlorine takes all the electrons and the sodium gives its one away. So we don't share, we actually have a negative charge and a positive charge. So let's just put that down, those kind of two extremes, because that's a good starting point. If we have Ionic bonds, this is what we had learned at the beginning. We did a lot of compare and contrast. And covalent bonds. The differences here are we had no electron sharing. And then over here with our covalent bonds, we had even electron sharing. And these, we could think of them being kind of like twins, right? So they're evenly sharing. Also on our ionic bonds, we have whole charges. And so what I mean by that is, say I'm looking at, let's see, I'm going to put it down here. Say I'm looking at sodium chloride. It's Na plus and Cl minus, right? Back when we talked about ionic compounds. And we could use our electronegativities, how much an element was attracting that electron, to help quantify the difference between these. So sodium's electronegativity is 0.9, chloride's was 3.0. So this is a difference of 2.1, meaning like this is super strong pulling electrons and this is very weak to pull electrons. So we could say that in our ionic compounds, we have large electronegativity differences between the atoms, right? And that leads to this positive, negative. Or if this is my scenario here, now the chlorine's going to take all the electrons, or just that valence one at least, and the sodium's left without any. Now at the other extreme was a covalent bond, and I'm going to give you as an example 2 hydrogens here, okay? These are like literally twins. And if I look at hydrogen, remember its electronegativity placed it right here. And so if I have a hydrogen connected to another hydrogen, this is 2.1, this is 2.1. Imagine my 10-year-old twins arm wrestling. They literally get stuck in a stalemate forever. They're identical, they're equal in strength. So if I were to draw a little bubble to show where the electrons were here, the electrons are very evenly shared between the two. No one's winning that tug of war for electrons. So when we describe our covalent bonds over here, we want to say we have little or no electronegativity difference. And we actually tend to quantify that as a 0, 2.4 difference. Over here, my electronegativity difference is generally going to be 2 or greater. So ionic don't share, covalent do share. Those are our extremes so far, but there's actually a middle ground. What if you have an electronegativity difference somewhere between 0.5 and 1.9? So you're sharing, but you're not sharing as well, okay? This would be like if my 17-year-old arm wrestles a 10-year-old, she's gonna beat them pretty well. So they're both kids, but one is a stronger kid than the other. So we wanna add a term here to my covalent bonds, and we wanna say these kind of covalent bonds, the ones we've been thinking about so far, are non-polar. And non-polar covalent bonds are where you don't have like a north pole, south pole. You don't have a electron side and a non-electron side. We have very even sharing in a non-polar covalent bond. We're gonna add a new category here because it's actually more of a spectrum. And we're gonna say in the middle are polar covalent bonds. So here are our new pieces. In a polar covalent bond, that's going to be like what we have in a water molecule. So here we still have electrons shared, right? So we have electrons shared, but it's uneven. Uneven electron sharing. And I'll say this is kind of like the cars at my house. I drive an old Honda Civic to work, and even though it's in both my name and my husband's name, I keep it most of the time. We also have a pickup truck that he likes because he's big, he fits in it better. And so even though it's in our names, both of our names, he keeps the pickup truck a little bit more. That's uneven sharing, where I keep it more or you keep it more. It's not 50-50, okay? So if we have uneven electron sharing, we could quantify that with our electronegativity difference and say this is going to be our electronegativity differences that are about 0.5 to 1.9. Bigger difference means more uneven sharing, so we even have a spectrum within this. And on these, over here I had no charges at all. I didn't write that down, but I have no charges at all. Here I have whole charges, right? Positive and negative. Actually, we had colored in our metals when we did this to say, hey, I've got that metal with a positive charge. With polar covalent bonds, like I have in water, we're going to see what we call partial charges. And that partial charge I can image in a few different ways. So let's just we're just looking at one bond here. So I'm just going to look at the oxygen and the hydrogen. So if I have an oxygen and a hydrogen, here's those two electrons, right? And instead of envisioning them as evenly shared, we're going to say, no, those aren't so evenly shared. And so to figure out who pulls them more often, who gets the pickup truck more often, I'm going to look here and look at their electronegativities, 3.5. And then hydrogen is 2.1. And so if I were to draw the electron bubble, we would have the electrons hanging out by oxygen a lot more often than they hang out by hydrogen. And as a result, what we see in nature, and then what we can symbolically put down here, is we see that I can draw a little arrow here, a bond dipole, to say that the electrons are going to hang out over here by oxygen more. So this side of the bond is a little bit more negative, and this side of the bond is a little bit more positive. I can indicate that word with either the arrow, or I can do a lowercase Greek delta and say partial negative and partial positive by the hydrogen. So we usually use either the arrow pointing to the negative side with a positive to say, hey, that's the positive, or we use these lowercase Greek deltas to say partial positive and partial negative. And there's a couple synonyms here. So this is, I would say, if I have this blue arrow, this is a polar bond, and that is the same as saying that I have a bond dipole, or two poles. So our addition on this page has been to say that our bonds are not all just evenly shared or charges. It's not just those two extremes. We also have these polar covalent bonds in the middle where electrons get pulled a little more towards one atom. And just a reminder, fluorine is my most electronegative element on the table. So the closer an element gets to fluorine, the more it's going to pull those electrons. So next up, we will look at how this impacts molecules.